Hello everyone, welcome to a review of 1 through 4 units, as well as Unit 6 in the AICE curriculum. Unit 6 is momentum, so it's technically part of these few units because they're actually really closely related. So we're going to be going over some MCQ problems. These problems are actually part of a quarter exam that I had in school. And we had 24 questions for around 45 minutes. So without further ado, I'll try and walk through my process of approaching these problems, solving these problems, using what I know, so it can help you for future problem solving type stuff. Yeah. Don't forget to subscribe, and yeah. So for number 1, the table shows some measurable quantities. Which row gives the correct order of magnitude of the measurable quantity in the stated unit? Okay, so basically what this question is asking is that which one is a realistic measurement for each one of these things, right? So first we have the mass of the coin, and they say it's 10 to the negative 4 kilograms. So let's try to make it into a smaller unit that's more tangible. If you ever seen in a lab when you were younger, this is like when I was in elementary school, but we had these little 1 kilogram weights that we had in a school. And these were actually really small and very light, but they were 1 gram. So definitely a coin is greater than 1 gram. I would say it's probably like around 17-ish, like 16 or 17-ish. But let's try and convert this unit into grams and see what exactly this measurement is. So we know that 1 kilogram is equal to 1 times 10 to the 3rd grams times 10 to the 4, because that's a measurement. And then we get that it's 0.1 grams. Okay, so if our coin is definitely greater than 1 gram, it's definitely greater than 0.1 grams. So it's most likely that A is not the answer. For B, we are measuring the thickness of a sheet of paper, and the order of magnitude is 10 to the negative 2, and the unit is meters. So if you haven't seen a thickness of a sheet of paper, I highly doubt it, like you're rage baiting. It's actually very thin, and if you actually seen it, it's probably around less than like 1 millimeter ish. Less than 1 millimeter, I believe. It's like you can't even see it, basically. But we can try and convert this meters into a more tangible thing. So we know that 1 meter is 1 times 10 to the 2nd centimeters, because there's 100 centimeters in a meter. And then multiply that by the actual measurement, and we get 1 centimeter. Well, turns out that we have 1 centimeter of thickness, but we know that the thickness of a paper is definitely less than 1 centimeter, or less than 1 millimeter. So this is most likely not the answer. The weight of an apple, 10 to the 0 newtons. So we know that newtons is F equals MA. And our newtons would be 10 to the 0 newtons, right? Is equal to mkg times 9.81, because it's asking for the weight, right? So we know that the weight is using F of g, which is equal to 9.81. And you get 1 over 9.81 is equal to mass kilograms. Mass is a variable, and then kilograms is the unit of measure. Just to be a little bit more concise. And it turns out that this is around like 1 over 10. So you get about mass is equal to 100 grams. And this is actually pretty viable. Like I said before, like a coin is 17 grams. It would make sense that like, I don't know, like 10-ish coins or maybe less than 10-ish coins is roughly the same as like an apple. So it's most likely C. But just in case, let's try and look at D. So the temperature of a person's body is 10 to the first K. Okay. So if you don't know, K is actually related to Celsius in the way such that K minus 273, I believe, is equal to C. So basically that means that when C is freezing, that means that K is actually 273. But if we look here, we see that 10K is the temperature of a person's body. This means that if we use this fact here and this quantity, basically what this choice is saying is that our body temperature is below freezing. And you should know that a body is definitely not below freezing, the core body temperature. So it's not going to be D, and thus our answer is C. Which pair of quantities contains both a scalar and a vector? Okay, so this is actually a pretty definition problem. I want to be honest, I didn't really know every single one of these. For example, I didn't know momentum, whether it was a scalar or a vector. But let's try and look at it. You can actually derive each unit and see if it's a scalar or a vector, but you do have to know some things that are scalars versus vectors. So you have to know that velocity is a vector because it actually has a direction along with its magnitude, like its speed. So speed is a scalar. So yeah. So acceleration, turns out that it's velocity over time, where v is a vector and s is a scalar. So in turn, v must be a vector as well. I should write vector out. Momentum is p, which is equal to kilograms times velocity. We know that mass is actually a scalar. So then velocity is also a vector, so then this also becomes a vector. And since we're looking for a scalar and a vector, it's most likely not going to be A because both values are vectors. And then we have momentum and moment. So moment, if you remember, it's force times the distance. We know that force is actually a vector, I'm pretty sure, because it tells you which direction it's going in. For example, if you're going forward, you might say it's positive. If it's negative, then it might be going the other way. But yeah. So then we have momentum, and we actually derived this before, so we know that this is also a vector. So both of these are vectors, so it's most likely not this. Kinetic energy. So kinetic energy is 1/2 mv squared. And turns out that I don't even know if this is a vector because although v is here, it's squared, so it's not necessarily the same, I believe. So we're gonna skip that for a second and then look at mass. So mass is actually kg. So kg is actually a scalar. So this might actually be viable if this is a vector. Okay, now that I re-look at it, it doesn't seem to be a vector. Because if we look at this equation, mv squared, typically the direction is conveyed in terms of sign for v, for example. But since it's squared, it doesn't matter which direction. If it's v or negative v or v, if you square it, they're going to be equal to the same thing. So this is not necessarily a vector. And thus, these are both scalars, and thus we're left with d by elimination. However, let's look at it just in case that we're not missing anything. So velocity is definitely a vector. Otherwise, we could not have deducted that acceleration was also a vector. Temperature does not convey direction. It's just telling the temperature of something. So this is a scalar. A micrometer is used to measure the diameters of two cylinders. Diameter of first cylinder is equal to 12.78 plus or minus 0.02 millimeters. Diameter of a second cylinder is equal to 16.24 plus or minus 0.03 millimeters. The difference in diameters is calculated. What is the uncertainty in this difference? Okay, so this is testing the uncertainty, specifically absolute certainty. So if we have 2.78 plus or minus 0.02 millimeters, and we're kind of subtracting this with the diameter of this. So it turns out that the rule is that you add these two together. You add these two uncertainties together since you have a binary operator like plus or minus, and you're working with absolute uncertainties. So you add these two together, and then you get 0.0. You get your diameters basically, and then the plus or minus uncertainty, 0.05 millimeters. So in this case, the answer is D. However, if you don't know the rule, try and think about deriving it. So let's say that our smaller value, we want to make it as small as possible, right? So we have 12.78 minus 0.02, which is equal to 12.76, right? And then we want to take our greatest value and add that. That's wrong. 24 plus 0.03, and you get that 16.27. And if you calculate this out, you get a difference, specifically 3.51. And then if you try to make it as close as possible, 7 plus this, 12.80, and then 6.24 minus 0.03, so you get to 16.21. And it turns out this is going to be 3.41 millimeters. Now let's say that there is no uncertainty, for example, right? So we're going to calculate the raw value. I'm ignoring the sign because we're just doing absolute-ish. So then this becomes 3.46 millimeters. And then we can see that it fluctuates between 3.51 as well as 3.41. So that we can say our uncertainty is 3.46 millimeters plus or minus 0.05 millimeters, which is our answer here. A sample of gas has a mass of 4.8 micrograms and occupies a volume of 1.2 decimeters cubed. What is the density of the sample of the gas? Okay, so if we look here, we can notice that this is in micrograms, this is in decimeters cubed, and then we're actually in kilograms per meters cubed. Okay, so it turns out that we have to write this out. So the grams we know is on top, divided by 1.2 decimeters cubed. So I'm gonna be completely honest. I forgot to memorize the metric system right before this exam, which is what I usually do. So I kind of had a guess on this problem. So first, let's get the quantity, the actual quantity, and then we'll figure out the tens. So we get 4 micrograms per decimeters cubed. So, like I was saying before, I didn't really memorize the metric system, but I do have some memory. So, if you know, in chemistry, AICE Chem, we use decimeters cubed to denote, I believe, liters, I think. So liters is identical to decimeters cubed. So, and then you know that like milliliters would then be equal to centimeters cubed, I think. Yes, so centimeters cubed. So you know that centimeters cubed is like 10 to the negative 2 to the third power. So millimeters is equal to 10 to the negative 6 meters. Yeah, meters. So then likewise, liters is equal to like 10 to the negative 1 to the third meters. So liters is 10 to the negative 3 meters. So then if we look at this, we get decimeters is actually meters cubed, or 1 per meters cubed. And then now we have to figure out the micrograms. So I know that it goes from kilograms, right? And then ... to grams. I know micrograms is smaller. So we have like hectograms, centigrams, milligrams. Milligrams is 10 to the negative 3. And then it goes to like pico, and then even smaller stuff. I forgot. And I'm pretty sure pico is like negative 9, 10 to the negative 9. And then micrometers is somewhere in between, and this should be around 10 to the 6, I believe. Actually, I think I lied. It turns out that pico is actually 10 to the negative 12, I believe. Yes, because pico is definitely the smallest of the smallest ones. Picograms is going to be 10 to the negative 12, and I believe like mu is right next to it, so it's 10 to the negative 9 grams. So if I use this fact, it's like 4 times 10 to the negative 10 grams over 1 minus... Oh wait. No, I was right before. So okay, so now we're gonna do micrograms. So I know that we have grams, so that's 1 gram, and then centimeters gram, it's like 10 to the negative 2 for centimeters, and then millimeters, and then it goes on to like picometers, which is 10 to the negative 12. And I know that there's also a nano and a micro. So the way I memorize it is that these actually go into 3, so it's 9, 6. So we have equals to 4 times 10 to the 6, negative 6 grams over 1 times meters to the negative 3, and get 4 times 10 to the negative 3 grams per meters negative 3. That's your answer, right? It's A, right? No, it's not, because we still have one more step to do, and that is to convert grams to kilograms. Because you don't always convert to the base unit. So we're going to multiply 1,000 grams times 1 kilogram, and we get 4 times 10 to the negative 6 kilograms meters to the negative cubed. And that is our answer, C. A stone is thrown horizontally from the top of a cliff and falls into the sea below. Air resistance is negligible. The path of the stone is shown. Which direction does the resultant force on the stone act during its fall? So we're looking for resultant force, and we know that this is in a 2D space, so there's only two forces, horizontally or vertically. So we know that air resistance is negligible, so we don't have to go into drag. So let's encounter the thrown horizontally. So we know the stone is thrown horizontally, but air resistance is negligible, right? So that means that there's no resultant force on the stone horizontally. And it stays at a constant speed, basically. However, if it's thrown across, we know that there's gravity pulling it down. So it turns out that our only force is gravity going down. Another thing I should note is that force is based on acceleration, right? So we can see that this is accelerating downwards. It's going steeper into the ground, or the sea in this case. So that there is actually a resultant force, but we can see that it's for each x, it's actually constant. So in this case, it's going to be D. So number 6, a car moves at uniform acceleration along a straight road. Oil leaks from the car at a successive rate of 1 drop every 2 seconds. The diagram shows the distance between 3 successive oil drops on the road. So, what is the acceleration of the car? Okay, so let's say that at beginning, our point here is going to be U, and then this point here is going to be V, where U and V are the velocities of the car. U is going to be initial, and then V is going to be the final. And then let's call this in between velocity W. So we can use a Suvat equation to denote the first part of this. So let's break it down into 2. So we have that the first displacement is going to be 9.0 meters. I believe it's U minus 1/2 at squared, or U is U minus 1/2 a, and the seconds in this case for each one is going to be 2 seconds. So it's going to be times 4. Actually, this is adding. Sorry, is equal to 9 meters. Then you get U is equal to 9 minus 2a. I should also say that I forgot a 2 in the beginning here because it's actually UT. So then U is equal to 9 minus 2a divided by 2. And then we can actually use the second part of this area. But instead, in this case, we're going to use V. So S is equal to vt minus 1/2 at squared, where s in this case is going to be 12. V of t is times 2v minus 1/2 a. T is going to be 4, or t squared is going to be 4. So you got 2v minus 2a is equal to 12. And we should also say that v is equal to u plus at, u plus 4a, where 4a is the entire thing, right? So we're relating the entire 3 drops, right? So 2 seconds, so 2 seconds and then 2 seconds, so 4 seconds in total. And then we get, if we substitute this into here, get 12 is equal to 2u plus 8a minus 2a. So then we get 6a plus 2u is equal to 12. We actually substitute this equation, so it's easier. 9 minus 2a plus 6a is equal to 12. And then 4a is equal to 3. And then we get that 3 over 4, or 0.75, is equal to a. And our answer is a. So basically we used Subat equations and we related the velocities of the drops, of the oil drops. So we took like the velocity of the car, related to the distances between the drops, and then we solved for a. In this case, it's acceleration. So yeah, our answer is A. A person of mass 60 kg stands on accurate bathroom scales placed on a floor of an elevator lift which operates in a tall building. At a certain instant, the bathroom scale reads 58 kg. Which row could give the person's direction of movement and type of motion? Okay. So one thing we should notice is that we're actually doing 58 kg instead of 60 kg. So let's consider this. Let's take an elevator and a person is standing on it. Let us say it's going downwards, which is conveniently the first one. Well, we'll try and reason through this. If we're moving at a constant speed, our character is not moving, right? There's no resultant force. And thus, the bathroom scale should read 60 every single time if it's at constant speed, because there's no resultant force. And thus, the weight of the person is still the same. So we can say that the constant speed ones don't work. Now we have to establish our directions, right? So we know that if we go downwards, our person is most likely to also go downwards, I think. Because if we're accelerating downwards, our person is moving downwards. And then we have f of g as well. So let's say this is the elevator movement. And this actually increases our weight. So then as a result, since we're looking for a lower rate, it's not actually going down, but going up. If you consider it, if we're going up, it somewhat cancels out with the force of gravity. The magnitudes are not to scale, by the way. So the elevator has some type of magnitude that reduces the force of gravity, and thus the scale is not reading your entire weight just because you're going up. The diagram shows graphs of various quantities plotted against time for an object dropped from a stationary balloon high in the atmosphere. Which statement could be correct? So graph 1 is acceleration against time, and graph 3 is a resultant force against time. Okay, so I kind of just jumped into the multiple choices. So for this type of problems, I usually just read each each answer choice and make sure that it's actually right. So A graph acceleration is 1. So this is acceleration, and we see that acceleration is actually a constant. So that means we're constantly accelerating, sorry. But if we're dropping an object, right, eventually we're going to be at terminal velocity, where this is F drag, for example, and this is Fg, and it's moving at a constant speed, and thus A is equal to 0 and not non-zero, because in this case A is equal to greater than 0, so it's not A or B. Graph 3 is acceleration against time, and then graph 1 is velocity against time, graph 2 is velocity against time. So these are the same for the first one, and we have to decide 1 and 2. So 1, let's say this is velocity, right? We can see that velocity approaches a certain value, which supports our theorem that it supports our theory that our object reaches terminal velocity and thus eventually reaches a constant value, which is evident in this case. In graph 2, we can actually see that our velocity is slowly increasing at a constant rate. This means that our acceleration is greater than 0, which kind of contradicts what we were just saying before, that eventually our acceleration will become 0 when this is actually never 0. So in this case, graph 2 is bad. Our answer is C. The velocity of an electric car changes as shown. What is the acceleration of a car? So we see that this is in kilometers per hour and this is seconds. And then the answer chosen are meters per second. So I kind of don't like these problems, but it is definitely one on the easier side. You just have to pay attention a little bit. So let's try and do this. So we know that acceleration is actually velocity over time. Velocity over time. And it turns out that in this case, our velocity is on top and our time is on bottom. So we can say that our difference in y, difference of x, is equal to a. And thus, we can say that our slope of line is equal to a. In calculus, you learn that you have a position, right? Position graph. Derivative of that, or the slope, is I wrote positive. The derivative of this, or the slope of position, is going to be velocity, and the derivative of that is acceleration. And these are all against time, so we can see that there's actually a very clear relationship with this. This is a slope. Acceleration is the slope of velocity, basically. Slope. So we just have to calculate the slope of this and then finally convert units. One way that you pretty much have to convert units is that the units are not homogeneous, meaning that they're not the same. So we can see that there's hours here and there's seconds here. So we have to read the graph here. Let's do the big triangle because it seems to end at a lattice point. So I don't know how many tick marks there are. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 tick marks per 50. So each one is 5. So then our velocity is 1.5 kilometers per hour per 4 seconds. So then move the hours to the bottom and then convert. And then you just plug into your calculator and you should get around 7.3 meters per second squared. The diagram shows P traveling at speed v about to collide with a stationary particle Q of the same mass. The collision is perfectly elastic. So we can see that P is hitting Q. Which statement describes the motion of P and of Q immediately after the collision? So one thing that should stand out to you is that this collision is elastic, meaning that momentum and kinetic energy are conserved. So let's calculate the PMMV of each answer choice. So we know that initially, how do I do this? P init, PI, let's say that's the initial, is equal to mass times velocity, where m is the mass of P and Q, and then v is the velocity as stated. And then our kinetic energy is going to be 1/2 mv squared. We're not going to do Q because Q is actually stationary, and since Q is stationary, its velocity is 0, and then the value is actually 0. So let's look at each answer choice, calculate their momentum and kinetic energy, and see if they equal the initial ones. So in this case, PF is equal to 1/2 V times M plus 1/2 V times M, because we can see that P and Q both travel in the same direction of this. So we know that they're both positive, and thus this is equal to MV. So this is actually a pretty strong contender so far, because we know that the momentum is actually the same. In this case, let's do kinetic energy of I. So we have 1/2 mv squared plus 1/2 mv squared. Actually, I wrote this wrong. Sorry. So 1/2 m, and then we're moving at half velocity, right? Plus 1/2 m times 1/2 the velocity squared. And then you actually get, I believe, 1/8 times 2, so it's 1/4 mv squared. And oh no, it's not the same. So in this case, A is not the right answer. For B, P comes to a rest and Q acquires speed v. So if we do v, PF becomes 1/2 times 0. Actually, there's no 1/2 times m. That's for P. And then Q will become v times m, or mv. Our kinetic energy is equal to 1/2 m. Our v is actually 0 squared plus 1/2 m, and then v in this case is actually v squared, so it's 1/2 mv squared. And oh my god, it actually matches. So we see that these two quantities for momentum and kinetic energy are the same, and thus this is overwhelmingly actually the correct answer. You can see this in the other equations, because we can see that the speed of 1/2 going the other way, and this actually negates the momentum. So if you want to calculate this out, the mv is here, the p momentum is equal to 0, which is not right, and then this becomes p is equal to negative mv squared, sorry. But those are why those answers are incorrect, just to give a reason. But we know that B has to be the correct answer, because these are just like, well, these have to match, and since these match, it has to be correct answer. Why? I'll cut it out. 你要跟我说啥？
我就睡觉了吧，11点半。
Yeah, 我还有2个 question. This is question 11. A ball of mass m moving at velocity v collides with a stationary ball of mass 2m. The two balls stick together. what fraction of the initial kinetic energy is lost on impact? Okay, so although we know, based on the question, the phrasing of the question, we actually lose kinetic energy. But based on momentum, you should know this, momentum is conserved with this collision because no external force is being acted upon it. And it is a closed system. So our momentum initially, let's say this is our m, moving at v, hits 2m, and then this becomes a system of 3m, moving at some u velocity, right? So let's actually write out this relationship. We get that mv, that's our momentum, plus 2m times 0, because we know that velocity is equal to 0, is equal to 3m times u, where u is the final velocity. We can divide by m, and we get that v is equal to 3u. Now let's calculate our initial kinetic energy. So this is initial kinetic energy. If we take this, right, so we have 1/2 mv squared plus 1/2 2m times 0 squared is equal to 1/2 3m times u squared. Actually, I kind of just wrote the relationship. But this is what these two should be. So this is initial, and then this is the final. And we have to find the relationship between these two, not necessarily equal. So if we calculate this out, we get 1/2 mv squared, and then we have 3/2m u squared. So turns out that initial kinetic energy lost, what fraction is lost? So we have to find the lost over total. So then we get 1/2 m v squared minus 3u squared over adding these two, 1/2 m of u squared plus 3u squared. And we can square these two. V squared is equal to 9u squared. These cancel out, and we're left with 9u squared minus 3u squared over 12u squared. Sorry, I made a mistake. It's not over, I misrepresented the total. So the total is actually the initial kinetic energy, because they're asking for initial. So you get 1/2 mv squared, and then we get you substitute inside, so 9u squared minus 3u squared 1/2 mv over 1/2 m times v squared 9u squared and it turns out that we get 6u squared over 9u squared, and we get 2/3. So let's just see. A uniform rod of weight 20 newtons and length 2.0 meters is acted upon two vertical forces as shown. What is the resultant force acting on a rod and the resultant moment about the center of gravity of the rod? Okay, so we can see that the vertical component of both of these the vertical component of the center of gravity, right, is here, right? This is in the very middle, and this acts down. So we know that the weight is actually 20 meters, 20 newtons. So this is 20 newtons. And if we use analysis of the vertical components, the up, y, is equal to 15 plus 5 is equal to 20 newtons. And then the down is y and 20 newtons. And since they're going in opposite directions, we subtract them. And then we get that the total resultant of y is equal to 20 minus 20 is equal to 0. So we know that C and D are automatically eliminated because we know that this is, not good. And then now we have to calculate the resultant moment. So we know that the distance between the center of gravity or the pivot is going to be 1 meter on both sides because they give us that it's 2 meters in total length. So it goes anti-clockwise this way, right? No, that's clockwise, sorry. Anti-clockwise is this way, which is shown by this 5 meters, 5 newtons. So it's 5.0 newtons times 1 meter, and get 5 newton meters. And then for clockwise, it's going to be 15 newtons times 1.0 meters is equal to 10 newton meters. And since we're only looking for the resultant force, we can try and figure out the difference between these two. These two actually go in different directions, and since we're calculating resultant force, we subtract them. Sorry, this is 15. We subtract them and find their absolute difference. So you get 15 newton meters minus 5 newton meters is equal to 10 newton meters. So in this case, our answer is A. So this concludes the end of this is the end of MCQ 1, review units of 1, 2, 3, 4, and 6. Thank you for staying to the end. Let me know if you have any suggestions in the comments of the video. Thank you.